All right, so take a look at example 8. Thank you. All right, so if an integral diverges, what does that mean? Diverges. Going to infinity or negative infinity, possibly, right? The symbol was this, right? Gets bigger, it's spreading out, and if something converges, then it's going to some finite number, right? Getting closer and closer too. So we kind of know when something diverges, when it's going towards a horizontal asymptote. Here are some helpful things that might help you if you're ever faced with like an integral that you either don't feel like integrating, or maybe you can't even find the antiderivative of it. If you have something that's convergent plus something else that's convergent, their sum should be what? It should be also convergent. Yeah, you can think of convergent as being like finite, right? So finite plus finite should be finite, right? So it's convergent. If you have something that is divergent plus something else that's divergent, and they diverge in the same manner, like positive infinity or both negative infinity, then what should happen? Should be divergent, right? Infinity plus infinity or negative infinity minus infinity is definitely infinity or negative infinity, and so that would diverge. What if you have something that diverges plus something that converges? Yeah, it diverges, right? Infinity plus 1, still infinity, so that's divergent. But of course, the one that we have to be careful about, and I don't know why this is still showing. There we go. The one we have to be a little bit careful about is if you have divergent minus divergent, and they're the same type of divergent. So infinity minus infinity or negative infinity plus infinity, what is that? Yeah, indeterminate. Okay, so that's when we would try something else, L'Hopital's rule, or try to rewrite it. Okay, so let's look at this one here. We got the integral from 1 to infinity, so we're approaching a horizontal asymptote, possibly, maybe there's not a horizontal asymptote, of 2 plus x over x squared. How would you go about integrating something like that? What could you do here? Can you do pattern recognition? It's a quotient. Remember, one of our strategies is simply to split up numerators. So that would be one way to do that. And remember, when you do that and you create multiple terms, you have to have parentheses around each of the terms. So that would look like that. And I'm not going to worry with the limit just yet. That, of course, then is 2 times 1 over x squared plus x over x squared is 1 over x. So very quickly here, without actually integrating it, when we distribute the integral and pull the 2 out front, the first one is a p-series, right? We're going from 1 to infinity, and we have 1 over x squared. So 1 over x squared from 1 to infinity would what? Converge or diverge? It would converge. To what will it converge without integrating it? 1 over x squared from 1 to infinity. 1 over 2 minus 1, which is 1. Yeah. So that would converge to 1, and then 1 times 2, of course, is 2. So the first term converges to 2, plus what happens to the second term? It diverges, right? 1 over x is that gatekeeper. 1 over x is the first, so that diverges. So now, just by kind of analyzing it, what can we say about the entire integrand or integral? Yeah, it diverges. So this could save a little bit of time if this were a multiple choice question. It could have like 3 numeric answer choices, and then one of the answer choices might be diverges. And you can figure that out just by looking at it or analyzing it. Now, here's another way to do it, and this is kind of what we're going to do when we get to comparison tests when we talk about infinite series. If you just take it as it is here, and you kind of simplify the leading terms, it's x over x squared, which simplifies to 1 over x. For large values of x, 2 plus x over x squared is essentially growing like a 1 over x by itself. And of course, 1 over x is the gatekeeper, and that would what? Converge or diverge? Diverge. So that's another way to do the analysis, right? Of course, you could actually, in this case, find the antiderivative of both and evaluate it, and you would get finite plus infinity. That's another way to do it. But for something like this right here, you've got from 1 to infinity, and you've got 1 over x, which is what? If you just looked at that term, it diverges, right? It goes to infinity, positive infinity. minus, 3x over 1 plus 5x squared. That one we're not going to be able to integrate because the derivative of the bottom is 10. I guess we could. Yeah, we could. 10x. We would be off by a 10. We'd have a correction of a 10th, and it would be a natural log rule. But maybe without having to do that, we wouldn't have to. What would this one effectively grow as? If you simplify the leading terms, x over x squared would be another 1 over x, right? It would grow just like a 1 over x, which is another infinity. And it would approach positive infinity, because 1 plus 5x squared is positive, and so is 3x for values greater than 1. So we essentially have divergent, which is infinity, minus divergent, which is infinity. So can we make any kind of concluding statement with this based on that? No. Now remember, all this time you could also be working on actually trying to find the antiderivative. But let's go ahead and do something here. Infinity minus infinity, if you recall, when we had indeterminate form, one of the ways to get infinity minus infinity into a quotient form is to simply get a common denominator, right? If you've looked at the worksheet, there's one in there where I kind of use a sneaky little trick involving the natural log to kind of condense it. And of course, we saw one yesterday where you condense it by using the properties of logs. So this one, if you just do your crisscross applesauce, it'll work. You got to start in the top left, though. So 1 times the bottom is 1 plus 5x squared. Then you take the middle sign minus the other product, 3x squared. So you got to start in the top left because subtraction is not commutative. All over the product, which I'll distribute, that's going to be x plus 5x cubed. And so if we simplify that, we get 5 minus 3, that's 2x squared, plus 1, all over a 5x cubed plus x. Now, if we were going to be actually interested in finding the antiderivative, this is probably not the best way to do it. Doing the two separate terms would be the way to go. But this, what's that? This does give us a better way, though, to evaluate it. Because now as a single quotient, I can look at the leading terms and simplify it. X squared over x cubed essentially grows like a 1 over x. And of course, a 1 over x would be what? Divergent. Yeah, divergent. So this one also diverges. So sometimes we can get the answer of divergent without actually finding the antiderivative and evaluating it. Now, if you came out with one of these to be convergent, it's probably going to ask you, like I did up here, if they converge, find the value. So in that case, you're actually going to want to find the antiderivative. But a lot of the times, just some initial analysis can get you to a divergent conclusion, which will save time and the possibility of mistakes and money. Time is money. Yes, Devin? No, on a free response, you could do that. You can make some argument that this integral grows for large values of x like this function, which also diverges, and therefore this function also diverges. Yeah, you could do that. Yeah, and we're going to be doing that particularly a lot with series when we get to chapter 9. And there's actually a comparison test. So we would make that comparison. Yes, yeah, you would write it with words, a statement, a sentence, yes. And you would want to throw this one in there. Compare it to that one, essentially. Yes?
So it doesn't matter that there's another plus x on the denominator?
Not for large values of x, right? Because if you remember, like back in the very beginning stages, the limit as x goes to infinity, I can have a 9999999 x to the fourth plus, or actually, let's make this a 0.00001 x to the fourth plus 9999999 x cubed. Now, in the early stages of x, for small values of x, the second term is going to be a lot bigger than the first term, right? But because we're going to infinity, the growth is going to be, in the end, dominated by the leading term. And any term that's not the leading term, yeah, it contributes a little bit, right? It contributes a little bit. But for huge values of x, we're talking about like unfathomably large values of x, the leading term always dominates the growth, right? It's like if you're fundraising and someone writes you a check for $1 million and someone else comes up and says, here's a penny. You're like, thanks a lot, right? But maybe that's all that person has. And they gave you all they have. So don't belittle them, but now you have $1,000,001, right? Cent. So it doesn't really contribute overall, but in their own right, they're special. So yeah, it doesn't matter that there's an x down there. We're just looking at the leading terms. Okay, good. Good conversation. We could do this because we're approaching infinity. That's the reason we could do this. Okay, so sometimes an integral can be doubly improper. Are we already there? Yeah, doubly improper. We talked about what that meant yesterday. I won't repeat it. So in this case, doubly improper is not necessarily, well, we'll just go with it. That's what it says. So if the integral from negative infinity to c and the integral from c to infinity are both convergent, then what can we say about the integral from negative infinity to infinity? Right. We can kind of do the travel agent problem. If we know that c is some value between negative infinity and infinity, and we integrate from negative infinity to that value c, and we integrate from c to infinity, and both of those are convergent, then if we have to find the integral of negative infinity to infinity, we can split it up into two separate types of infinity by using c as our layover, as our connecting flight, and then we can add the results together. So in this case, convergent plus convergent would be convergent. And so that's what we're going to have to do. If we look at example 9, really easy to see that it's an improper integral. But we've got infinity on both of those. And so on a free response, notationally, we actually have to split it up into two separate integrals. So the choice is ours, and we've got quite a few things from which to choose. I need a value from something between negative infinity to infinity, but here's the kicker. It has to be an x value that's in the domain of the function. We don't want to like stop at like another discontinuity. Well, our function is 1 over 1 plus x squared. What's the domain of 1 over 1 plus x squared? All real numbers. So pick a number. What's a good number? Negative 52,765.3? What'd you say? 2 would work. 2 is fine. What'd you say over here? 70 would work. 550 would work. Any number would work. So if you want to choose your number that you volunteered, do it at your desk. I'll do a different number up here, and in the end, we should end up with the same result. Okay? I kind of like Gorell's number. When we evaluate limits, really, the nicest number to plug in, if you don't like a challenge, right, is 0 if it's in the domain. And 0 is in the domain. So 2 is not bad, 70 is not bad, but I'm going to choose 0. So the first thing I'm going to do is I'm just going to write this as negative infinity to 0 of 1 over 1 plus x squared dx plus 0 to infinity of 1 over 1 plus x squared. Okay, so 0 is just some arbitrary value in the domain, but it's a very convenient value. And now, of course, I can evaluate them. Now, if this were a multiple choice question, I would probably still recommend doing this, but you wouldn't have to worry about the limit. Now with the free response, notation. So the limit as, I'll say b goes to negative infinity of the integral from b to 0 of 1 over 1 plus x squared dx, plus the limit as, I would probably stay away from b. Even though I've used it in the first term, I can maybe reuse it over here. But I would choose a different value, like, have we used q yet? Let's use q. Why not? Capital Q. As q approaches infinity of the integral from 0 to q of 1 over 1 plus x squared. Just stay away from x in this case, right? All right, so now we can evaluate it. What is the antiderivative of 1 over 1 plus x squared? It should just jump right in your head, right? It's not the natural log of 1 plus x squared because there's no x on the top. So it's arctangent. Good. So this becomes the limit as b goes to negative infinity of arctangent of x from b to 0 plus the limit as q goes to positive infinity of the same thing, arctangent of x, but now from 0 to q. And we have 2 to evaluate, but we're not ready for the limit yet. So again, we have to bring that along arduously. Arctangent of 0 minus arctangent of b plus limit as q goes to infinity of arctangent of q minus arctangent of 0. So these things aren't real difficult, but there is a lot of writing. Okay? But it's not like you're having to think too much as you write it down. Just be careful. All right, so I'm running out of room, so I think what I'll do here, since we have that, I'll just shrink it down, make more room. All right, so then now it's time to evaluate And I got the limit as b goes to infinity, and I got arctangent of b. So now it's time to kind of remember what the graph of arctangent looks like. You remember what it looks like? Yeah, it kind of looks like, well, it kind of looks like an S, but it's got horizontal asymptotes, right? At the top at pi halves and at the bottom at negative pi halves. So as I go out to the left, plain old arctangent of x is approaching negative pi halves. Yeah, just a real quick review, because it's one of the ones you need to know. That's the graph of arctangent. There's pi halves, there's negative pi halves. So as I go to the left, it's negative pi halves. And now negative pi halves times the negative one that's there makes that plus pi halves. And then arctangent of 0, well, you can use the graph for that as well. It passes through the origin. So tangent of 0 is 0, so arctangent of 0 is 0. So that evaluates the first term, plus doing the same thing over here, evaluating the limit as q goes to positive infinity of arctangent of q. That ends up being positive pi halves minus arctangent of 0 is 0. Now, of course, we were going through all of this notation so that we could get full credit on a free response. Can we stop here on a free response? Yeah, that's numeric. Yeah. But I'll keep going. Pi halves plus pi halves is 2 pi halves. Good. Yeah, excellent. I like that. 2 pi halves. Good. Okay. Also known as 4 pi fourths. Or pi. Yeah. Pi. Pi. Half a pi plus half a pi makes for a happy man who likes pie. Too bad pie's not cereal. It's today's National Cereal Day. Do they make pie cereal? Maybe so. At some point, maybe they did. Yeah. I know they made Oreo cereal at one time. They made Tim Duncan cereal at one time. Wasn't that good? Do they? Like the Thin Mints and stuff? Well, what I usually do is I just buy a bag of Thin Mints and I dump them all into a bowl and fill it with milk. I eat it. So I can make my own cereal. You can make cereal out of anything, really. Right? Just add milk. Eat it with a spoon. Okay, so this one actually converged. Is it surprising to you that this one converged? Or could you suspected that in the beginning? Yeah. This is kind of growing for large values of x like a 1 over x squared, which is a p series, with p equal to 2, which is greater than 1. We're going out to not only the right horizontal asymptote, but also the left horizontal asymptote. And if it converges on one side, it's got to converge on the other, in this case by symmetry. So you actually could have used symmetry here. Because the function is an even function, you could have integrated from 0 to infinity, maybe saved a little bit on the notation, and then doubled it. Okay? You got to be careful when you double infinity, though, or infinite values, because they're not always the same type of infinity. But in this case, they would have been. All right. Can we use symmetry here, now that we brought it up? Is our integrand an even function? No, it's not. So anyway, you want to try and do this one, MC style, multiple choice style? Sure? Because, I mean, do you think you could pull this notation off again on your own, or should we just do it? You could do that? Okay. So let's try it MC style. What is the domain of the function? That's what we want to get in the habit of doing. That's the same as x over e to the x squared. We can divide by 0. Is e to the negative x squared over 0? No. E is 2.7. You're never going to take a numeric value, raise it to any power, and get 0. So the domain is our numbers. So what can we use as an intermediate value? Yeah, 0 works nicely again. So we'll split it up from negative infinity to 0 of x e to the negative x squared plus integral from 0 to infinity of the same thing. And again, we're going to just avoid the limit notation here. So, yeah, do we need to use integration by parts for this one? To integrate it? No, we don't. No, we don't. Because notice e has an inside function of negative x squared. And what's its derivative? Negative 2x. We get the x. We're only off by a negative 2. So we could do this one by pattern recognition. So if we're off by negative 2, we'll have a negative 1/2 correction. The x gets packaged back up in the exponent. And now the rule of integration is the outside function, e. What's the antiderivative of e? E, right? So e to the blob is e to the blob. We'll evaluate it from negative infinity to 0. Plus, same antiderivative here, negative 1/2 e to the negative x squared, this time from 0 to infinity. Okay, so when we plug in, again, I'll keep my negative 1/2 out front, beefy bracket. Plug in the top, I get e to the 0, that's 1, minus e to the, now I got to be careful here. When I plug in negative infinity squared is positive infinity, times the negative 1 still makes it e to the negative infinity. And I'll come back and evaluate that later. I don't want to do too much. Plus negative 1/2 factored out again, or I guess we could just say minus 1/2. Now plugging it in at the top, we get e to the negative infinity squared minus e to the 0, which is 1. Can we stop there on a free response? No. If we did that, we would lose points for not having a limit, and we would get points for not having a numeric answer. So, no, bad choice. But, of course, what happens to e to the negative infinity, or same thing as e to the negative infinity squared? They go to what? They go to 0. Yeah, so we end up with negative 1/2 times 1 is negative 1/2, minus negative 1/2 times negative 1 is positive 1/2. Ruh-roh. What happens? We cancel. Oh my goodness. This function was not an even function. But is it odd? Not peculiar, but origin symmetric? If you replace x with negative x, do you get the exact same thing? Well, no. Okay, but do you get the opposite thing? You do get the opposite thing. Okay, because this one doesn't change and they're multiplied, that x is an odd factor. This is an odd function. It has origin symmetry. And if you remember, I said if you have an, yeah. No, the bell curve has y-axis symmetry, and it's a power of e, but it's e to the negative something over the square root of 2 pi. It's the standard normal curve. But this one is origin symmetric. And if you remember, I said if you ever integrate an odd function over a symmetrical interval from negative 5 to 5, negative 10 to 10, it'll always be 0. Does it work from negative infinity to infinity? It did this time, yeah. And it's only because the infinities are the exact same size. And so in this case, we really kind of have infinity minus infinity, and it did, in fact, equal 0. So, yeah, it worked in this case. And we just proved it. So that's how you would contend with infinities on both ends. Free response, a little bit more burden on the notation. Has to come from a limit process. Multiple choice, probably still want to split it up. Choose 0 if you can. If you're going from negative infinity to infinity, we haven't seen any yet that have discontinuities on the interior, so we'll have to deal with that later. So if it's continuous everywhere, choose 0. A little bit easier. Okay, this one says calculator permitted. Skylar's reading ahead, or maybe not, maybe he's thinking ahead. Okay, calculator permitted. Find the area of the region bounded by this graph and the x-axis. All right, this graph is what? Even, odd, or neither? It's even, right? There's only one x in it, squared, so positive or negatives are going to be the same. What is the limit as x goes to infinity? If you plug infinity in, you get infinity squared, which is infinity, times negative 1 is negative infinity, divided by 2 is negative infinity. What's e to the negative infinity? 0. E to the negative infinity is 0. So I know that there's a horizontal asymptote, and it's going to approach it on both sides. It's a y-axis symmetric function. What's the y-intercept? What do you get when you plug in a 0 for x? You get 1 over the square root of 2 pi. So this graph should look something like this and something like that. Oops, symmetric. We want to figure out what the area under the curve is. So how do you want to slice it, vertically or horizontally? Please say vertically. Yeah, thank you, vertically. All right, horizontally. Okay. So we'll set it up. We abbreviate area AREA. Remember that? Area. It's going to be the sum of the infinitely thin slices from left to right, which is from negative infinity to infinity. of the top curve, which is 1 over the square root of 2 pi, e to the negative x squared halves, minus the bottom curve, which is 0, right? dx. Now, the reason we're using the calculator on this one is because e to the negative x squared can't find the antiderivative of that, okay? But we can certainly use the calculator, right? Now, I could use symmetry here if I wanted. It looks like I could integrate from 0 to infinity and double it. So let's go to the calculator. Math 9. Actually, you know what? I'm going to put the 1 over the square root of 2 pi out front. It is a constant multiple, and they need to take their rightful place outside the club, right? They can't come in. This is a variable club only, right? Ah! Okay. Y'all are fast. All right. Math 9. And then where's infinity on your calculator? Is it just an 8 that you wait for it to tip over? Oh, a really big number, like 10? 100? Oh, very small number. Negative, how about negative 99? To 99. Of E second ln. Hey, it's relative. Remember the guy that only had a penny? Imagine if he had 99. That's huge to him. Okay? It's all relative, Colin. To the negative x squared. You and your big numbers. Me and my big numbers. Do not judge. Right? We just came out of advisory. All right. Did I type it in correctly now, folks? But for my tiny big numbers? Yeah, let's see. 1. Is that the right answer? It actually should be like 0.999. This is breaking the calculator but not getting punched in the face by the calculator. This is breaking the calculator and letting it tell you what the answer is. So let me back off, Colin, to a smaller big number of just negative 99. Ah! Still 1. We're still breaking the calculator gently. Remember, E goes to the x-axis muy rápido. E to the x squared, más muy rápido, right? So, man, let's go ahead and come back with a smaller big number. How about negative 1? Oh, I don't need, yeah, okay, I know. Y'all are fast. Yeah, y'all aren't as quick to compliment. I hit graph. Okay. All right, so now we get 0.68. So now we can kind of see some movement. 0.68, it's approaching 1. If you would have gone like really big like Colin, I think you would have broken the calculator. Let's see. Okay, and get punched in the face. 999. 9. Negative 999. You got to put the same ones there. See, there you go. Yeah, that's a punch in the face. Okay, so it turns out that the area under this curve from negative infinity to infinity is equal to 1. This is called the standard normal curve. Right. It's the curve that they use in statistics to determine probabilities. If you go out to the concavity change values, what do we call those? I forgot. The inflection points. If you go out to the inflection points, which of course we can find, second derivative equal to 0, 68% of the population will fit in between there. So you can then get into p-values, which stands for probability values. And there is a calculus-based statistics so that you don't have to look at those mind-numbing tables of p-values, which basically give you areas out at a certain point. Upper tail, which by symmetry you could use lower tail. But really, you could, if you wanted to, you could just integrate from wherever you want to wherever you want, and you can do it using calculus and get the same p-value. Yeah? The values in your integrand. Well, remember the z statistics, right? Are those the normalized ones? Yeah. When we turn it to a z statistic, that's how we normalize it, and then we can look it up in the table. Yeah. So if you ever take statistics, you will encounter this curve. It's a very, very, very important curve in statistics. And because 1 translates to 100%, that's 100% likelihood. So that's why it was normalized. That's what it means, so that the area, it was adjusted so that the area under the curve would equal 1. And it is the bell curve. It's also known as the bell curve because it looks like a bell, right? Here's a little bell dinger. Ding, ding, ding. See? And now you're hungry for tacos, right? No, you weren't, but now you are. And now I said bell taco, and you're like, French fries. Anyone had these spice seasoned Mexican French fries with nacho cheese? They're not that good? You thought they were okay? Yeah, that's good. If everyone liked the same thing, everyone would be after my wife. Good thing. We all have, right? Right, good thing we all like different things. Okay, sweet. So yeah, there's the standard normal curve. Pretty neat, pretty cool. Calculus-based statistics is a real thing. Okay, so remember I talked about comparison tests when we get to series. You've heard a lot about these series, but you don't know what they are. This is kind of going to be the same thing. It's kind of the same idea, but with integrals. So let f and g be continuous from some a value inclusive up to infinity. Let's also say that we have a function g of x that is greater than or equal to f of x. So it's either bigger or the exact same thing, and they're both non-negative. They are 0 at the very least or positive. So essentially, we have positive functions and we have one function bigger than the other for all x in the interval from a to infinity. Then let's see. If the integral from a to infinity of g of x converges, meaning we get an unbounded region that's finite in area, what can we say about what can we say about the integral from a to infinity of f of x? Keep in mind, f of x is a smaller function. Can we say anything conclusive? If we have a certain function that goes to the x-axis fast enough, okay, and therefore converges, then any function that is smaller than it, let's just think about values. If you have some function that goes to something finite, then anything smaller than it should be what? Finite or infinite? Yeah, you're not going to have something smaller than finite be infinite, right? That's not how things work. If you have something that's finite, anything smaller than finite is still finite. So kind of the same idea. If the bigger function, g of x, from a to infinity converges, then the smaller function on the same interval converges too! Exclamation point. Okay? That's a comparison test. Less than finite is also finite. That's essentially what that means. Yes? Okay. The next one. What if f of x, and remember f of x is the smaller one, what if f of x diverges from a to infinity? We have something that now diverges. What can we say then about something bigger than it? It diverges, because diverges means infinity, and anything bigger than infinity is infinity. Good. So these are one-way tests. They only work one way. If the big one converges, the smaller one converges too. If the small one diverges, the bigger one diverges too. Those are the only conclusive things we could say. What if the big one diverges? Can we say anything for sure about the smaller one? No, because smaller than infinity could still be infinity, but it could also be like 1, right? Going back to the guy with the 1 penny. It could be 1. So it's inconclusive. What if the smaller one converged? What if the smaller one is finite? Then can we say anything about the bigger one conclusively? No, because bigger than finite could be finite, right? Like the guy who has 2 pennies and rubs it in the other guy's face. Or it could be infinity, right? The guy who has infinitely many pennies, and he tries to pay with them in front of you at the store. Seriously, dude? Have you heard of a credit card? Right? You ever been behind someone at the store and there's, I think I have some change in here. Right? You're in the 15 items or less, which is supposed to be fast. Right? You got 16 items and you're paying with coins. All right. All right. Do you think when they have 16 items and the 15 items or less, Do you think it's a math problem, or do you think it's an English problem? Do you think they can't count, or do you think they can't read? Or neither? And then, yeah, it could be neither, right? Sometimes when I first started teaching, believe it or not, it's kind of funny. When I first started teaching 20 years ago, every teacher on campus got a box of business cards. You know, like when I built homes, I had business cards. It made sense. But when I was a teacher, I got a business card that says, Kevin Corpy, math teacher, New Braunfels High School. I'm like, great, a whole box. When am I going to use these? When can I envision myself handing a math teacher card to someone? And I thought, if I'm in line at the grocery store and the 15 items are less, and the guy in front of me has 16, I can flip it out. Here you go. I can help. I'm a math teacher, right? I can't think of any other situation where I would use those business cards. So I still have a full box of business cards. They quit giving them out because then they realized, you can't really use them. I guess if you go to sometimes at the restaurants, you could drop your business card in the bucket and they draw it out for a free lunch, but we can't leave for lunch anyway. Because we're not students. Oh, good. Great. You can't leave either. Great. Just remember that next time you see some students sneaking away. Bad choices, consequences. Right? Yeah, either way. Okay, example 11. Ready? Here we go. Example 11. If 0 is less than or equal to e to the negative x squared, which is less than or equal to e to the negative x. Okay. It says so. I believe it. For all x greater than 1. Woo, for 1. Okay. Not between 0 and 1. Then determine if this integral converges or diverges. It goes to the x-axis faster. No, that's all right. I am too. Okay? Now, your intuition tells you, heck yeah, that converges, right? Because they're going from 1 to infinity. Remember, if it grows faster than 1 over x, it's going to converge. That is exponential, and it's exponential to the x squared. So we know it's going to converge. So if this were a multiple choice question, and it was like one of those multiple choice questions, which might say which of the following integrals converge, and then you have Roman numeral 1, that. Roman numeral 2, something else. Roman numeral 3. And all you have to do is decide if they converge or diverge, and then pick either 1 and 2 only, 1 and 3 only, 2 and 3 only, 1 and 2 and 3 only. I don't know. Then you don't need to know the value to which it converges. You would say this converges, boom, done, answer. But if it's a free response, and these do show up sometimes as a free response, you can't just say goes faster than 1 over x. You have to kind of prove it. So there's 2 ways to do that. You can either find the antiderivative and evaluate it and show that it's a constant. We can't do that for e to the negative x squared. But maybe if we could find another function, since we know it converges, we suspect it converges. So if I want to prove that this converges, I need to find a function that is what? Bigger or smaller than it? Well, we got an argument now, bigger or smaller. Well, let's think about it. You said it first. If I can find a function that's bigger, and I can show that the bigger one converges, then this one being smaller would have to converge. If I found a smaller one that converged and this one's bigger, then I'd be like, I still don't know, but I had fun, right? So we do have to find a bigger one. Man, where do we go to find a function that is conclusively bigger than e to the negative x squared without having to prove that it's bigger? Look to the left. Oh, sweet. I love that left vision. I'm going to use that left vision more often. E to the negative x dx. Okay, so this one, we can't just say that one converges by eyesight, right? We got to prove it. So what's the antiderivative of e to the negative x? Negative e to the negative x. Now notice I haven't rewritten the definite integral with the limit yet, have I? Which is okay, as long as I do this at this step. The limit as b goes to infinity. So I haven't done that yet. I've always rewritten the integral. But if you want to skip one step of writing, you can go to the antiderivative, call it b there, and put the limit in front, because it has to come from a limiting process. Is this a limiting process? This is a limiting process. So let's evaluate it now. And I'll keep the negative up front, so I get e to the negative bth power minus e to the negative 1th power. And now I'll evaluate this. And of course, we know e to the negative b as b goes to infinity goes to what? It goes to 0, so negative times negative. This becomes e to the negative 1. And then we could say, so the integral from 0 to infinity, 1 to infinity, of e to the negative x dx converges. Okay, so now we would say, so since e to the negative x squared is less than or equal to e to the negative x, they gave that to us, but we still have to state it as part of the reason. So since, okay, comma, the integral of 1 to infinity of e to the negative x squared dx converges, what? Also to, as well, additionally? What do you want to say? As well. Okay, good. As well. Exclamation point. Right, there you go. So that is the ingredients of a comparison test. We've kind of done that with the squeeze theorem, right? Kind of the same idea. We show that a function, in this case that is bigger, converges. And we knew we were looking for a bigger one because we thought about it. And it converged. So now we have to state the inequality. We're showing that the inequality they gave us is not just some arbitrary thing, but it's relevant. The one we found is bigger than the one that we were given. And so by the you don't even have to say by comparison. You could just say, so this one that we were given has to converge to. Now, does it converge to e to the negative first? The one that we don't know about? Does this one converge to e to the negative first also? No. Could it? I mean, yeah, very unlikely, right? Because it did say less than or equal to. But I'm pretty sure it's not. I'm pretty sure it's something that is wider than this. Smaller, right. How much smaller do we know? We don't know, okay? We just know it converges. We knew it converged by intuition, but this is like a math proof. It's proving that it converges, all right? So that's the comparison test. Let's try it again on example B. Determine if the integral from pi to infinity, whoa, okay, of 2 plus cosine of x over x converges or diverges. And notice they didn't give us an inequality. Yikes. It's real convenient when they give you an inequality. It's kind of like, here, compared to this one. All right, so we have a little bit of thinking to do, right? And that's why intuition is so important. By intuition, do you think this integral is finite or infinite? Do you think it converges or diverges?
I don't think it does.
You don't think it does either? What do you think it does? Is there another option? Well, you think it oscillates. Oh, okay. Yeah, I don't know if we'd call that divergent. We would just say that the integral doesn't exist. Okay, well, let's think about it. What is the numerator doing? 2 plus cosine of x as x gets bigger. It is oscillating, right? It's oscillating between 1 and 3. How did I know that? Yeah, it's shifted up 2 and the amplitude is 1. So it's going down 1 from 2 to 1, up 3. So it's pretty much hanging out between 1 and 3. I'm always a 1 or 3 or anything in between, right? So even though it's oscillating, it's between two fixed numbers. And so it's essentially a constant, right? And then, of course, the denominator is x. So we can really kind of pull constant multiples out front, kind of, right? But it's not a constant multiple. It's an interval of constant multiples. And so we're really kind of looking now at just 1 over x, which would do what? Converge or diverge? 1 over x would diverge. So your intuition should actually tell you, based on how I kind of talked you through it, that it diverges. Your intuition should tell you that it diverges. Now, if that were x squared in the bottom or x to the 1.1th power, I would suspect it converges. But because we have a constant interval over x going to infinity, I think it diverges. All right, so for comparison, I need to find an integral that is whatcher than this. Well, if I found one that was bigger, and I said the bigger one diverges, then the smaller one may or may not diverge. I don't know. I need to find one that is smaller. If I can find one that's smaller and say the smaller one diverges, then anything bigger than divergent has to diverge. So I want to find one that is smaller than 2 plus cosine of x over x. One over x, yeah. So the choice is not given to us, but it should be something that's relatively obvious. 1 over x is less than or equal to 2 plus cosine of x over x for all x, and I'm going to use theirs greater than or equal to pi. We know this, right? Because when you multiply the numerator by some number bigger than 1. Now, if the numerator was possibly a 1/2 at some point, that makes it smaller at certain times. But we judiciously chose this to be a low point of 1, which sometimes makes it equal, and a high point of 3. So for sure, the one on the right now is sometimes up to 3 times bigger, sometimes it's equal, or anything in between. So we don't have to prove that, we just have to say that. And why did I say for all x bigger than pi? Because that's where we're starting. Okay. So now, I just need to figure out then, what is the integral from pi to infinity of 1 over x dx? Now here you could say it's a divergent p series. Even though we're not starting at 1, the p series has to start anywhere greater than 0. When it starts at 1, that's the time we have the summation formula, 1 over p minus 1. So you could either say A, this is a divergent p series. And then you'll just say p equals 1, which is less than or equal to 1. Or B, you'd actually have to evaluate it, right? The antiderivative of 1 over x is the natural log of the absolute value of x. We'll take the limit right here as b goes to infinity, and we'll evaluate it from pi to b. Okay, and if you do that, you'll end up with infinity. So either way. And notice the part A, as kind of Devin inquired earlier, part A is more of a verbal argument with words. Part B is a mathematical argument. But once you show that diverges, now you've already showed the inequality, right? So you just go straight to the answer. The integral of 2 plus cosine of x over x dx from pi to infinity does what? Diverges. We used as well already, so how about 2? Yeah, it diverges 2. Yeah? Okay, that's all we have time for because it's advisory day. So we'll pick up with 11C tomorrow. Make sure that you are chipping away at the worksheet. As we move faster and faster, I'm noticing fewer and fewer worksheets are coming in. So try to keep up. It's BC, best class ever. Have a fantastic cereal day.